All right, so I'm Valentin. I've been working in the video game industry for more than 10 years now, out of which 4 at Splash Damage in London, United Kingdom. Now, Splash Damage has a rich legacy. It started way back in 2001 with Enemy Territory, then Quake vs. Enemy Territory. Brink, you might know us from that game. Then we switched to Unreal Engine Power Games. We help a bit with the Batman Arkham games. We had our own free-to-play shooter called Dirty Bomb. And you might know us recently from our collaboration with Microsoft at the Gears of War franchise. So what are we going to talk about today? This is a bit of the agenda. We're going to talk about how we structure our teams and projects, how we set forth creating standards, and most importantly, how we validate those standards. And then we're going to move into compilation, continuing with unit testing, automation, and good stuff like that. And then at the end, we're going to talk about the so-called Splash Engine and how do we merge that with the latest UE4. Just a bit of a disclaimer. So we're here to share some of our learnings. Some of these are from our AAA projects, but most of them are from like prototypes or like various secret sauce, game projects we had, or our cumulative UE4 experience. And feel free to find some inspiration, agree or disagree with some of the techniques that I'm going to show you today. So we're about 300 employees, and we're split across multiple ongoing projects at various stages. Some can be full AAA, some can be prototype, and so on and so forth. And some of these projects use the Splash Engine, which at its core is just vanilla UE4 plus a couple of our own enhancement fixes and stuff like that. We're going to cover this a bit later on. Right. So how do we start setting the foundation of a game, starting with the game modules, the project layout? So we have a master Perforce server that allows us to do nice merges within the projects. That's the root of it. Then we have, let's say, Project A, Game Project A, which follows a straightforward structure. There's a couple of documentation folders or like the raw assets. And then you might know the traditional UE4 folder structure, the engine, and the game project named the same as the master game project. So in this case, Project A, Project A. And so on and so forth for other projects. And then we have the Splash Engine, like the master root of Splash Engine. Now, we strive to have multiple game projects as opposed to one big monolithic catch-all module. Why is that? Because it helps with good architecture, encapsulation, allows fast iteration. You kind of isolate your changes to, you're working, let's say, on the weapon, you just touch the weapon module, let's say. So that allows faster hot reload linkage. And also promotes reuse. Some of these game modules, maybe they get so good that you want to reuse them across. If we take a bit of an X-ray vision in this structure, let's say you have this generic component, and you have a module called runtime, which is the game-facing one, where all the business logic resides. Then you might have testing that allows you to validate this logic. Then you might have editor-only modules for like some enhancements on the UI side of the editor only. Or you might have interface, which is just header files like glue between multiple game projects. And going a bit into depth, this is kind of well known. There's the Unreal Build Tool specific file with some dependencies and like some defaults there. Then you have the implementation part and the interface part. And then so on and so forth. I mean, this is, traditional UE4 folder structure. But it still can get a bit hairy to do all this. So we have a quick way to automate this. It's just a glorified batch file that allows you to say, do you want an editor module? Do you want a test module? And it will create a folder structure for you and put in some sensible defaults. So just a batch file can get a lot of quick wins easy. All right, so you have this nice folder structure. How do you go about filling it with good code? Well, good code is supposed to follow good coding standards, right? And in Splash Value, one of our core guiding principles is mastery, especially when it comes to C++, and we try to be careful about the way we architecture our code. Now, we didn't have an established coding standard. There were some attempts at documenting these practices, but they were like scattered around in various documentation places. What's wrong with this approach? They grow big, they grow out of date, it's hard to maintain them. They're usually in a separate location. You have to go out of your way to like, oh, how is this supposed to work? So from the code, you're supposed to go in the documentation, and then only the gods of programming get to like do the coding standard. And who are we kidding, right? Nobody has time to read documentation. You just code. So at Splash Damage, I pioneered and the guys helped me to have a different approach, where the standards are actually source code files. So you can actually affect the build by messing up with the coding standard. So because it's live source code, it means it can participate in code reviews. And I'll talk about this. And it has a system for easy reference and searching. So going into a bit more detail, there's just two main files. A H file, which shows the more architecture and layout of your classes, and a C++ file, a CPP file, which deals with more in-depth C++ rules. They sit under game side code, and recently we open sourced them, so you can check them for yourself in GitHub and see if you agree or disagree with some of the choices we made there. This is a bird's eye view of the standard. I hope everyone can read it. Going a bit into detail, you can see there's like a combination of these islands of heavily commented areas and islands of actual source code that show you a bit of how you should architecture stuff. And then it's either UE4 guidelines. In this case, you see there's some various tidbits about how you should structure your classes, or it can be about how you should write the actual C++ code. So in this case, it's something about how you should use good rules for your destructor. Going back, you see there's this nice tag system. Everything inside square brackets, it's used for quick reference or searching or referring to that particular piece of code. So in this case, brackets class.virtual refers to the rules about how you should structure or combine together the overrides or like virtual methods. Or in this case, the ecs.gc refers to the portion of the rules that's supposed to guide you about how you should structure your objects, like you should refer them with weak pointers and stuff like that, or true U properties. Or like how you should combine together, in our opinion, the replicated variables with the replicated functions, and so on and so forth. Now, the best usage of this is through code reviews. This is a screenshot from Perforce's own code review tool called P4Swarm, and this is me telling someone you should use the class.member definition. And the good rule about this is like it takes pressure a bit from the code reviews. It's not me dictating to the guy because I know better. It's because we all agree to follow these common rules, right? So it's easier, and everybody knows what we're talking about when I'm saying func.arg readability or something. So the standard itself is continuously evolved like that to code reviews. Normally, you would send your piece of code to one or two colleagues. A change in a standard you would send to the whole team, and if you get enough upvotes, that makes the new standard. Now, a funny unintended consequence was that, remember, because they're real classes, there was like how we structure character classes. Turns out you can actually instantiate the coding standard actor in a scene and add a static mesh to him. So I think in this case he's preparing to fly away. Maybe he saw some dodgy code or something. All right, so equally important, content standards. Why is that? Because Poor practices lead to poor results, right? It will compound over time, you will lose productivity, you will have huge cook times, deployment times. And also the UE4 editor is relatively easy to modify to kind of add productivity enhancements to it. So the ground rule we follow starts with naming. If you have good naming, everything else follows nicely. So every asset follows kind of this structure. There's a base name and then a prefix. And this already leads to less confusion, better searchability. The prefix part, it just uses initialism from the class name. So if it's a static mesh, it will be SM. If it's skeletal, it will be SK, and so on and so forth. Here's a couple of examples how you should, how we encourage people to name their assets. So you see the nice prefix like T for texture and a bunch of suffixes to make it more clear. Now, another type of assets are blueprints, and these are kind of content codes. So they follow the same idea as a coding standard. They live on the game content side, and they're just basically nicely laid out blueprints with like nicely formatted parts and lots of good comments and tooltips showcasing the techniques that we want to follow. In order to further drive this a bit, we have some validation, and the best use case for this validation was like it forced people to be to comment out their blueprints. All right, so you have this content stuff, but how do you go about validating and making sure that they are actually followed? So this happens primarily in the CI and the build farm. You either get validated after you submit or more complex checks during nightly builds. And primarily there are three ways we validate: the naming I showed you, the blueprints, and more general asset validation. So the naming validation is just a small editor commandlet that kind of uses that initialism rule to see if, you have a texture, it should be T, and a couple of manual whitelisted exceptions. And also, more importantly, we disallow naming stuff like test or error or warning, because you don't want to go into logs and be confused. And an interesting thing that goes a long way of helping with this is that we intercepted the way you do new materials, new stuff in the editor. So here I'm creating a cube map texture, and it already creates a nice initialism for it, so I can only concentrate on the name, taking out the guesswork. So this already leads to good practices. Now, another interesting thing we did, we disallowed random imports of data. So you shouldn't import your stuff from the desktop, then you send it to the recycle bin, and then you're like, oh, where was that master source asset? So you should put them in a raw folder in source control and only import from there. A small but important rule we follow. Blueprints validation, again, a small editor commandlet just checks if there's some tooltips, if you have at least one common node, if you didn't name your nodes like new function or new item, whatever. We didn't go too much in depth with this. If you have the chance, you should try the Epic's own blueprint compiler, which is way more complex, and maybe you can leverage it to check more complex rules. More general asset validation, like everything from your textures, models, physical assets, and stuff like that. This is done on the CI, on the build machines, and primarily checks for missing or bad references and ugly stuff that could hurt you during cook times. Also importantly, it disallows referencing stuff from developer or like test folders, because a lot of people kind of do their small experiments in their own personal space, and then they forget about this, and then they just link it into production, and that leads to a lot of problems. So we disallow this, and we catch it early. So we found an interesting kind of system to allow this. And we actually leverage the cooking process. And literally, we cook everything by elevating the warnings as errors. So anything that would slip under the carpet, that you will disregard, now it's immediately an error, so you get a chance to fix it immediately. Now, obviously, there's some caveats here. This might not scale well for already big ongoing projects on a cook all, and all your asset could take like days. That's why it's important to have this as early as possible in your prototype stage. If you start doing this in production, it's a bit too late. But I still advocate for it. And if you do it later in the stages, you should look into other ways, maybe leveraging the asset registry to kind of walk the dependency and see if there's problems there. But still, this got us very big benefits. The cook all, I'm going to show you how it tied in with pre-commit. All right, so let's move into actual compilation. Obviously, hardware plays an important factor here, right? Either you cook, either you compile, either you build lighting. So we kind of discovered like a rule of thumb is like, yeah, the more hardware threads you have, the best. Obviously to a point, so 8 to 16 is really nice, 16 to 32, but after a point it kind of plateaus. There's no longer a benefit investing in faster hardware. We also experimented with distributed compilation. You can either use off-the-shelf solution like Incredibuild, which are very easy to use, but they're relatively expensive, so you need to budget for them. We also tried FastBuild, which is an open source alternative, and you can find integrations on GitHub, although the onus is on you to maintain it better. I keep talking about this CI system, the build farm. It's actually several build farms depending on the project. If you're a prototype, you only get one machine. If you're a full production project, you might get, I don't know, 30 machines, your own mini cloud. Interesting here, like the best kind of configuration we had is the AMD Threadripper, the first generation. We didn't look into the second yet. That's a good bang for your buck. It does a full rebuild of 421 in under 15 minutes. What do we use to orchestrate all this? Primarily, we use TeamCity, but lately we started using Jenkins as well. That's why it's important to use the so-called architecture as code, because we want to be independent of the orchestrator. Why? Because in the past, we were too ad hoc with this, and it didn't scale. For example, too tightly, everything was like in TeamCity, so good luck moving it out. Too specific for a project. If you have another project, you need to do everything from scratch. Good luck if it breaks and try to debug locally. So that's why now we're leveraging Epic's own BuildGraph system. What is BuildGraph? BuildGraph is just an alternative to the traditional batch file scripts that do your cooking and deployment. It's just an XML-based infrastructure of scripts. And this allowed us to have good reuse. Like if you condense all your major operations into a set of codified scripts, that promotes standardization and like good reuse. And also another interesting thing we did, we unified all the calling paths. So everything uses BuildGraph. Like Epic itself uses it, but they didn't do this. And we went a step further. So no matter if in Visual Studio, in the command line, on the build farm, everything uses the same system. So if you modify a flag, it will get modified once, not in like 10 places. It's quite powerful after the box. You can, Epic provides a couple of good examples. They use it to distribute, I think, the engine themselves. So yeah, if you want to get started, there's some good information there. We modified it quite a lot ourselves. And the most we got out of it was like preparing the editor binaries to send out to the team. So again, a nice bird's eye view. If we go in closer, you see it has documentation. It can include other scripts. It has a bunch of variables that you can set up and configure. And pretty much the core idea is like these agent nodes that can run commands. And the commands can be various compilation things. I'm building some cook dependencies here, like the crash reporter. Or can be just various general commands like zip, unzip, move files, delete files, stuff like that. So you unify everything in this one recipe, rather than having a bunch of batch files everywhere. let's talk about pre-commit. In my opinion, is like I wouldn't work on another project which doesn't have this system. A bit of context before. So generally, we follow the trunk-based development, which means there's one main line for each project. So we split off only for like major releases. That means that everyone collaborates nicely. There's one place of truth. There's less overhead, faster iteration. But the downside is like breakages have big impact because if you break something, the whole main line dies. So your traditional workflow would be you code for a bit, you hopefully review your changes, then it goes to the main line, and only then you have the validation from the build machines. Now, a better system is the following. You start coding, like usually, you review, but then you kind of go sideways and you do a personal type of validation. Was this validation successful? If no, you have this nice chance that now you just return to the user saying you done goofed something, went bad, so you have a chance to fix it. If it was successful, only then you submit to the main line, and then it gets picked up by the more general validation. So effectively, there are two systems working here. There's a front end that the coders use, and there's the back end, what the build machine does. The front end is just a glorified tool that allows you to indirectly submit or do kind of personal builds. And you can do off-the-shelf solution. If you're using TeamCity, JetBrains provide a Visual Studio plugin for this. If you're using Jenkins, there's support out of the box for pre-commit, but only on Git. Or if you have a small tools division, you can try to write your own. Either if you try to write your own or like get it off the shelf, it basically looks like this. Two main choices. At the top, you choose what you want to check against, and at the bottom, you see in the yellow there, only submit this if the test was successful. So that means on the back end, it's just a nice personal build system. Obviously, the more configuration you put, the better it is because you have better chances to know that you didn't break anything. But at the same time, you might have more stress on the build farm. So it's nice, balance. You have to be careful there. In order to help with this, we came up with a reasonable kind of infrastructure for this, whereby to kind of cut down on the compilation time when you do this pre-commit tests. So the idea here is like you rebuild kind of overnight all the participating configurations, and then throughout the day, you just incrementally build, reusing this kind of cache that you have on the build machine. So for example, I want to test the editor, I want to test the game on PC, and then the game on another platform, let's say PS4. Normally, to rebuild this from scratch to know that everything didn't get affected, it will take, let's say, even 2 hours on the fastest machine. So I do this overnight, I leave the object files there, and then every day a new developer participates with his changes, and he will do a non-Unity incremental build, and that kind of cuts it down to like 3 platforms. You can check them in 15 minutes. Obviously, it depends on the extent of your changes. If you modify the engine.h, then you're paying for it. But still, it's quite good. So the takeaway here is like, this was a major productivity booster for us. We experimented with a project for a year and a half, I think, and now we're spreading it, we're evangelizing to the rest of the projects in the company. Obviously, it's not a silver bullet solution, but still it helps quite a lot. Let's continue more on this theme of automation and testing and how can we help creating good system that help the developers. Now, still into the commit territory, it's because we're using Perforce and you have history, it's nice to have a lot of info there, but nobody wants to write so much stuff every single time. So we did a couple of tools that help like the developer, in this regard, like adding tags, links to your Jira, or like title and description. And it kind of looks like this. It's just a glorified UI that allows you to kind of take the guesswork and just concentrate on description, tagging, and adding whoever bodied your code. on the other side, what happens when you want to validate this commit? You want to make sure, again in Perforce, that they follow this formatting. Interestingly enough, we experimented with time of day. For example, we were cutting off the commits after like 5 p.m. to like discourage commit and runs, or like let a bit time to test. Or most importantly, you don't want to put fire upon fire. So if the build is broken, nobody can submit unless you have a special build fix token. So this is how it kind of looks to the user. Like Perforce shows you this nice dialogue saying that I did a couple of action and rules, but the last one was not safe. Like the build was broken at the time, so you're not a fixer, you cannot submit. So this is another kind of nice way to kind of gate and make sure people kind of follow nice procedures. Now, the black sheep of game dev, unit testing. Everybody loves it, but not that many people use it. Now, Epic themselves, they have a good framework. So there's good stuff to start and use already. We enhanced it a bit. We follow the given when then structure. Of course, we have separate coding standards for this test as well to show you how to write. And because they're in Visual Studio, it's very easy to kind of, how should I write my unit test? Oh, I don't know, I'll just bring the unit test standard. I'll kind of look a bit, and then I'll get an idea. They're integrated with our orchestrator, like for TeamCity. And also we did a bit of setup and tear down support, like you can create programmatically a small world, you can spawn actors in it, and then it will automatically be destroyed. So let's take a nice little example of how would you write a unit test in the splash damage framework. You start by having a couple of like sugar, syntactic sugar macros to kind of have your flags, your namings, groupings, and stuff like that. And then you're ready to just start writing the unit test in one line with a nice name, and then you can concentrate on the logic. So for example, given that a character has an attached actor, when you set the team ID on this parent character, then you expect that the child actor has the same team ID, so you test for that. So in a couple of quick operations, you just have a unit test, and hopefully you write more and more of these. We also experimented with functional testing, which this is a bit more involved. Needs some special setup in the editor, like some specially crafted levels with like blueprint actors in them. They live on the content side. They follow Epic's own conventions, but they're not network capable. So depending on your needs, they might not be so useful. We didn't go too much into detail, but now there's a new system starting with 420, I think, called Gauntlet, which allows to kind of have various functional scenarios in a client and server architecture. So check this out if you're so inclined. Now, if you're writing tests, and like I showed you earlier, you have this nice separation between the runtime, the gameplay logic, and the test. Obviously, the test module, you need to test the actual internal logic implementation. But at the same time, you want to access this private data, but only from the test, not from the rest of the other modules or the games. You don't want to leak the implementation details. So our solution was to piggyback on those module API things. If you're familiar with this, if you write your game modules and you need to interact with them, you have these decorators like module name API. So we added a new one which has test. So for example, if I have a player runtime component and somewhere deep in his implementation there's this camera target component. When I declare this, I use the player test API. And then in the equivalent player test module, when I want to test something about this camera target component, I just get it for free. I can just interact with it. There's just a bit of magic you need to do in the C# file, in the build definition, saying I want to use there's just a Boolean flag. You say, I want to use this thing, and you have it. And in this way, it's nicely encapsulated. No other game modules can access this. So you still are nicely contained. And this is an example of a couple of tests running on TeamCity, and they're all OK. This is just like you need to, the log that the testing framework produces, you just need to kind of map it to what TeamCity needs. Now, this was covered very nicely in a previous talk yesterday, but it's quite an interesting way of automating your workflow. The Unreal Game Sync that is used to distribute the game binaries. So you want to have a nice system, a nice control system where you distribute binaries across. And this is especially useful if you want to have this concept of last known good rather than always working on the tip, like on the latest. Latest can be broken, even with all the tests, let's say it's broken. So you want to send out the last known good that someone, either a QA or like some automated system, marked as good. So this is very useful for non-programmers. We did a couple of modifications to this Unreal Game Sync. Again, we kind of leveraged the build graph, and we had more control on it, how you prepare these zip binaries, you insert crash report into it, and so on and so forth, and then you send it out. But largely, it follows what Unreal Game Sync does out of the box. So I recommend using this system. So I guess the takeaway here is you want to invest in automation. It brings very nice wins later on, but do it, if possible, early in the lifetime of a project, if possible, even in the prototype. Don't leave it all the way into full production, because the project will have too much inertia. You can still add some stuff, but it will be harder. Okay, what about Splash Engine? So in our work, we try to extract and reuse the stuff we do in Unreal Engine. And this is pretty much just things that become kind of game agnostic, enhancement and fixes to the engine. Or we have some nice UI component library, some audio one, a nice event system that kind of decouples the listeners from the broadcasters, so they don't need to know from each other. Asynchronous tasks, some small rendering features, take art utilities, and so on and so forth. Right? That's the kind of the collection that makes Splash Engine together. So the majority, they get seeded from Splash Engine, and integration happen in two ways. Either like downstream, I call it, when you want to merge the latest UE4 happenings in the engine and then in the projects, or the other way, like a project gets such a cool feature that you want to bubble it up to the engine and then to all other projects. So if we take a closer look, again, this is our Perforce from previously. We have just a collection of like the drops that we get from Epic. This is Splash Engine, and this is where the actual game projects live. And then the Epic drops is just a flat collection of whatever you download from Epic. Splash Engine has an interesting format, though. There's this clean branch. I'm going to show how this works in a second. There's the main line, and then there's various staging areas for every particular projects we have. So in order to understand this better, let's take a merge scenario. Let's say I want to update a particular game project to the latest UE4 version. Again, you start with this structure. Then you take from the latest drop, you copy across into this clean branch, and this gives you nice incremental diffs. Only after this, you merge across into the main line of Splash Engine, and this is the chance to kind of fix any conflicts or like fix up plugins. For example, we sometimes use Wise for audio or Houdini. So this is your chance to bring those up to date as well. Now, in the meantime, Project A evolved at its own pace, right? So it's time to bring the latest developments of Project A into the staging area, which is kind of abandoned since the last integrate. After you've done that, you're free to separately do this merge from mainline, which is now latest UE4, into the staging area. And you can work here in nice isolation, solving conflicts as you go. and hopefully you do it fast enough so project A doesn't, evolve too much, because you cannot stop the development. You cannot just say, oh, guys, I'm going to merge now. Don't do any more work. So you work in the staging area, and this allows us, I think the fastest we did was like 2 weeks. So after you completed the merge in the staging area, then you're free to move it out and merge into the actual game project itself. And hopefully it didn't evolve too much, that you might have some conflicts, last-minute conflicts, but they're not that many. The bulk of the work you already did. So you see the takeaway here, this system kind of allows us to have nice, quick integrations. Decouples like the integration work from the main dev work, but it needs to you have to be careful, because having a structure like this needs some dedicated resources, otherwise it kind of atrophies. So we have a small tech sharing group that kind of takes care of this and tries to always have this ready. Like, for example, that main line, all that stages, they need to have their own build machines and stuff. All right, so we're nearing the end of the talk, so I'm going to leave you with a nice kind of cautionary tale. So we did the 421 integration following all these recipes. So we ate our own dog food. We did pre-commit. All our tests ran. Everything was nice. We gave ourselves a pat on the back. And then when the game project was ready, we asked the guys to continue their work. And then they opened the editor. And then they found out that every single static mesh got turned into one triangle, which is the best optimization ever. But because nobody figured to actually, after the merge, test the actual level. So I guess the takeaway here is like no automation system would save you from having good due diligence. But I think this is the best combination. Having a nice plan that you follow, and then complement that with nice system, nice automation system that catch errors as you go. And with that, that's it. Thank you very much for the opportunity. And this is Splash Damage. Check our website and GitHub.